All right, we've got a few people here, so I'm gonna just start drawing some graphs. I'll start explaining it once we get a few more. Let's see. So I can kind of narrate too, if that's helpful. So I'm just gonna be drawing like the sine graph, the cosine graph, just some basic stuff. Because I think the thing that's really getting y'all is probably infinite limits. So let's start with the basics. All right, so let's take, for example, a tangent graph. So we know that tan at 0 is 0. So the tangent graph is going to look like this, these S shapes right here. And each period is going to be 1 pi. So this is pi here. So this is negative pi. Oh, just kidding. Pi over 2. So then we're going to have another one at pi. Yeah, so what's the right? I just said the right thing, drew the wrong thing. And this is going to be 3 pi over 2. And then plus negative pi. Okay, so this is just basic. This is a basic tangent graph right here. You should remember this probably from either high school or if you took trigonometry / pre-calculus at Kennesaw, you probably looked at this as well. So we obviously know that tangent at pi over 2 doesn't exist, right? Because if we think about the unit circle, right, we know that pi over 2 is this point right here. This is pi over 2. And if you remember from the first session, we know that tan equals sine over cosine. And if you remember this from high school, this is just a bit of trivia. You don't really need to have this locked into your brain, but it's something you can put together if you have context. The radius of the unit circle is 1, so we know that sine is going to be our y value, cosine will be our x value. So if the radius is 1, then that would make this point right here 0, 1. And then since tangent equals sine over cosine, and we know that sine is y, cosine is x, 1 does not divide by 0. So we can't do that. So that's why we have to use a limit from either the left or right side to truly get a good idea of what's going on here. So we'll start with the pretty simple one. The limit as x approaches pi over 2 from the left side for the function tan of x. So this limit is going to be from the left side, so let's take a look over here. So pi over 2. So as you can see, the limit, by the way, like the answer to this should be a y value that it's approaching. So this is an asymptote, which means that the tangent graph is never going to cross that. So our limit for tan of x as it approaches pi over 2 from the left side is going to be positive infinity. So this right here, like you kind of have to know the general shapes of these, but I'm not going to make you guys sit. I'll do the harder ones. So I'll do all the weird ones like tangent, secant, cosecant, and all the ones that will have infinities we'll draw out today. I'll explain each one. Let me get an eraser or something here. It's gross. I'm not using my towel. This will work. Okay, so keeping all of this in mind, I'm going to leave this part up and then just erase the surrounding bits here. Because if you know just this John, I'm pretty sure you guys know this bit, but like you shouldn't erase all of this because this is gonna be the same axes slash scales of axes for each function. Because when we're looking at trig functions, we really only care about what happens in the period between -2 pi and +2 pi. Other than that, we don't really need to know all that much. So the next one I'm going to do will be secant of x, which, if you guys remember correctly, secant of x is equal to 1 over cosine of x. Or we could just say it is the inverse of cosine. So keeping that in mind, I'm going to redraw this pi over 2 here. -3 pi over 2. Just giving you as a generalization here. So we know that the cosine starts here at 1, then goes down to -1, up to 0, and finishes at 1. So this is a cosine graph. Oh, not that part. That was a mistake. There we go. Something like that, right? So it looks like this. Please excuse my poor drawing. I'm not an artist. But you get the idea here. You get the general understanding of the idea. So the next thing we'll be looking at is the secant graph, which I'm sure you guys remember this from trig, but this one's a little bit stranger. So this one, what we need to do here is we're going to be looking at the tops of the graphs. So we're going to be looking at minimums and maximums, which basically means like the dips here, the humps here, like we're just looking for this point, this one, and then this one. So if you can draw a cosine graph, you can draw a secant graph. I'm going to erase this because I'm assuming everyone's had time to look at it by this point. And I'm going to rewrite all of the properties. I'm just going over some graph stuff right now, just because I think this is probably the best way to learn this stuff visually. So now we want to draw the secant. So let me change colors for that so it's not super duper confusing. But the secant is going to be like this. It's going to be a parabola going the opposite direction of each hump and dip. So I don't have a lot of room on my whiteboard there, but you get the general idea here. And like I said before, these dotted lines, they're acting as asymptotes, which means that our y value will never cross them. So now if I asked you for the limit as x approaches, let's see, pi over 2 from the right for the function secant of x. All right, does anybody know the answer to this question? I'll give you guys a little bit of time here to just take over your idea. So we're going to be looking at this asymptote, and we want to know what the limit is as secant is approaching the asymptote from the right side. You can just comment it. You can put it in the group chat. If no one knows, that's also okay. Just let me know so I don't have to sit here and ramble. Where did I put my telephone? I need to be looking at this group chat. Okay. So negative infinity, that is correct. Very good, very good, yes. So as you guys can tell, it's just basically for these infinite limits like this, we're going to be using the asymptote in whichever way the line is going along the asymptote. So if it's going down for this, it's going to be negative infinity. If I asked you for secant of x as it approaches pi over 2 from the left side, then that would give you positive infinity. So it's not bad at all. Our answer is going to be negative infinity here. Is everyone okay with that? Let's see. You guys both said negative infinity, so you're both correct. So Now, what we're going to do is we're going to look at the next function. I'm going to give you guys a second, just look at this. It's really just a cosine. If you can draw cosine, sine, and cotangent, you can draw all the other graphs. So if you know your basics, your fundamentals well, then this should not be super duper tricky for you. If not, I would highly recommend downloading Desmos on your phone and looking at graphs as much as you can, because you truly should have, gosh, I'm trying to say this without, I don't want to scare you guys or anything, but you should definitely have a good understanding of how the graph shapes look and all that. If you don't know what you're, if you just understand the algebra, that's great. I'm scary good at algebra, but you need to understand the graph shapes in this class as well, because a lot of these concepts, especially when we get further along in the course, are going to be, it will make sense algebraically, but let me put it this way. It's much easier to check your work with a graph than it is algebraically, because there was one question in the third test in Calc 1. This was 2 years ago. I worked the entire problem. It was a 3-part problem. It took up 2 pages to work. And on the third part, I got that wrong because I dropped the negative sign at the very beginning of the problem in the first part. So if you don't know what this stuff looks like, it's going to be harder for you to understand it, because, calculus, the algebra can get very, very tedious and very repetitive. So if your algebra isn't stellar, it's going to make calculus a lot trickier to work with if you don't have a graph understanding. If you understand both, then you are not going to have too much of a hard time in this class. But when I say understand, I mean you really got to know it. So pi over 2, pi, 3 pi over 2, negative pi over 2, negative pi, negative 3 pi over 2. Also, if you're afraid of fractions, you're going to have to stop that, because I'm sure you guys have figured out from the homework that calculus has a lot of fractions. Yeah, that's right. Okay, so this is y equals sine of x. This is just the basic graph for sine. So now, keeping in mind that same logic we used with cosine, we are going to do the exact same thing to get cosecant from sine. Wait, you know what? I'm not going to go back on my word. We're going to keep those in different colors, because I think that is going to be a lot nicer to look at. And if there's one thing I've learned from doing ridiculous amounts of math, it's that if you don't enjoy looking at it, you're not going to enjoy doing it. Because math is inherently pretty to look at, but not if you're not good at it. Which is what I'm here for, to make you guys good at math and enjoy it. So I'm going to give you guys pretty math to look at. So this is y equals sine of x, and then the blue is y equals cosecant of x, which is just, of course, we know that cosecant of x equals 1 over sine of x. So now let's do another limit example. Limit as x approaches, let's do a weird one. Negative pi from the left side for the function cosecant of x. Okay, so negative pi from the left side. So our answer is positive infinity. I don't want to make you guys answer all these because these are kind of the very similar thing to the last one, but we're through the graph part. Cotangent, if you remember the tangent graph, it's the exact same concept as this. It's going to be actually cotangent. The only difference is that instead of, no, I'm going to draw that one too. Because you know what? Why be a slacker? We have been in quarantine for so long. Sometimes it's just nice to do stuff. Okay, so cotangent. So this one, I'm not going to draw the tangent function because it's not really needed. Cotangent here, what you're doing is you're starting on pi over 2. So you're starting on the ones that have the denominator of 2 for your S shape. You're going to go like this, that, this, that. This is going to be negative pi, and this is going to be positive pi. So that's cotangent, which is just the inverse of tangent. And if you guys remember earlier, I said the reason that we had to express it as a one-sided limit for tangent was because pi over 2, or tan of pi over 2, doesn't exist because it ends up giving us 1 divided by 0. And as we know, we can't divide by 0. So then the next thing we're going to look at is going to be cotangent of pi over 2. So this is just some basic trig rules right here. We know that tan is sine over cosine, right? So then we know that this cotangent is the inverse of tangent, so it's going to be cosine over sine, and that's going to give us 0 over 1, which is why we are allowed to start there, because 0 divided by 1 is just simply 0. So now we've got all of the graphs drawn. So I'm just going to give you guys the algebra, but I wanted to make sure you guys really wanted it. So I had to make you sit through the graphs first, because you guys don't get the pleasure of doing that in person with calculus, because that's pretty much this entire class, just watching professors draw graphs and hoping that you'll understand the graph. But I don't like to rely on hope when it comes to math. So I just figured I would give you guys all of the math that I am able to give you. So if you really don't like graphs, you can memorize this. And I'm now allowing you to memorize this, because if you've gotten this far, that means that you have looked at the graphs at least. But I would really just say to you, advise that you should probably not memorize this, because it's going to be a lot better for you to know the shapes of the graphs already. So it's better to think of this stuff visually than it would be to do just by memorizing it. Let's see, secant of x, pi over 2 from the left is infinity. I don't have them memorized off the top of my head, because I just kind of have to think about the graph in my head, but it's nothing horrible. Plus now you guys have this, which you guys are gonna soon realize how useful this is. Let me turn on some lights. I don't know if you guys are having trouble seeing this or not. Okay, that's not plugged in, neat. So now let's see, limit as x approaches 0 from the left for cosecant of x is equal to negative infinity. Yeah. As x approaches 0 from the right for cosecant of x is equal to positive infinity, and limit as x approaches 0 from the left for cotangent is equal to negative infinity, and limit as x approaches 0 from the right for cotangent is positive infinity. Oh, and also, since you guys stuck around, I just actually literally just thought of this, but this is kind of a neat trick. If you're having trouble with this stuff and maybe you just aren't a visual learner, but look at the in behaviors here, right? So if we look at every single little in behavior, and yes, I am going to circle all of them because I want to and I can. So look, this in behavior is coming from the left, but I wouldn't think about it in left and right. I would think about it as positive and negative. This one's negative, so tan negative becomes positive infinity, tan positive becomes negative infinity, secant negative becomes positive infinity, and then secant positive becomes negative infinity. And then you'll notice that all the ones with the C, the in behavior is going to be the same as the limit, for the sign at least. And this is just for trig, don't apply this to other stuff, but this right here, if you want to break it up, you can absolutely do that for a little memory trick and say, if it starts with a C, so we'll just say starts with C for trig. I'll write that as a little footnote because I know some of you someone's gonna find something weird that starts with a C, or I don't know, I'm just gonna avoid error. Why put that in your hands when I can keep it in mind? Start with C for trig, then the in behavior, we'll say in behavior. Oh, and here's something for you computer science students. If then in behavior sign equals infinity sign. And of course, I'm referring to positive or negative. So there's a little trick. If it starts with the C, the in behavior. Oh, here we go. If it starts with the C for trig, if it starts with the C, the in behavior is meant to be. Something like that. I don't know. I'm sure someone can think of a more clever rhyme than I can. But that's just basically all of the trig in behaviors right here. If you want to get one more look at it. This right here, they don't even really have this in your textbook anymore, but I saw this in my textbook my freshman year and I thought it was useful. So I've copied it all down, wrote it down word for word, and I have actually referenced that page more than anything else because that is the one thing that everybody forgets. Like that is, when I do SI sessions for Calc 2 even, they all forget this because limits is a very short portion of calculus. So it's pretty understandable to forget it. So the next thing we're going to look at is asymptotes, which we kind of already did, and I kind of just want to teach you guys some fun math now. So is everyone here comfortable with that, like with what we just went over? Because I think if you guys are ready, I'd like to start some basics of taking derivatives and all that. Simple yes or no. If you guys want me to move on to derivatives, let me know. If you want me to stay on limits a little bit longer, just shoot a topic in the live chat comment thing for what you want me to cover. Or just say derivative if that's what you want me to do. Okay, no one's responding. Nice, there we go. Perfect. Okay, I'm going to go over some basics of derivatives and we'll start with just some rules. So I've already been over this just once, but I'm going to reiterate the power rule because it's very, very essential. So power rule. Power rule states that if the derivative d dx for the function x to the a equals a times x to the a minus 1 power. And this is relevant to any polynomial statement. So for instance, if we had 3x to the fourth plus 6x squared plus 2x, then we can apply the power rule to this entire statement and solve it quite quickly. So I'll start with the 3x to the fourth power. So we're going to bring down the fourth out here and then subtract 1 from him up there. So now we've got 4 times 3x, and 4 minus 1 is 3. So now we're going to do this one. So plus, we're going to take the 2, multiply it by the 6, which is going to give us 12x, and then we're going to reduce the power of the x by 1, which will just give us x, because anything to the first power is going to be itself. And then right here, so we're going to take, there's a 1 here, right? Because x is just x to the first power. That is indeed a fact. X equals x to the first. So we're going to bring out that 1. 2 times 1 is just 2. Then x, we got to do 1 minus 1, so x to the 0th power. This is an exponent rule. Anything to the 0th power is 1, so this is just going to be 2, because 2 times 1 is just 2. So our final answer, we'll multiply out that, will give us 12x cubed plus 12x plus 2. And I know you guys are using some silly homework software that is going to say that's the wrong answer. So I'm going to do it their way, not because I want to, but for you guys. So we can factor out the 2 of this statement. So this is also equal to 2 times 6x cubed plus 6x plus 1. If you really just want to be a perfectionist about it. So that's the power rule, just the basics. That should be pretty easy to comprehend, I think. And I went over that in like one of the first sessions, so I'm just giving a quick reminder before we hop into some fun stuff. So now, one of my favorites is the product rule. Ew, handwriting. Oh well. Okay, so the product rule is the way that let's say we've got a function like x squared times 2x plus 3. So if you want to take the derivative and multiply it out, then you can do that. Sure, that works. But if you multiply it out and then take the derivative, you can just use the power rule and view it as a polynomial expression. But for the sake of learning this, I'm going to explain it to you guys the way that it's meant to be taught. So if we view this as f of x and this function as a separate function, g of x, now I'll write that out just so it's a little more clear. F of x equals x squared, and then g of x equals 2x plus 3. So if we want to take the derivative of this, the way we would go about that is we would do it this way. So we take f of x times g prime of x plus f prime of x times g of x. So this right here is called the product rule. Basically what it says is if we have 2 terms that are being multiplied together and we want to take the derivative, then we will take the first term. We'll say I'm going to use f of x and g of x just for the sake of simplicity. If you don't understand it, then I'll find a different way to explain it. But for now, so if we just take f of x, we take the first function f of x, leave it as is, multiply by the derivative of the second function, which is g of x. So we multiply it by the derivative of g of x. Then we do that same thing except flipped. So we got f prime of x, which is the derivative of f of x times g of x. And then we take these two and we add those expressions together, and that will give us our derivative. So let's take our little example here and solve it. So x squared times g prime of x. So that's just going to be 2 for the derivative of g prime of x, because we know that. I'll write that out too, just because this is probably how you should be approaching these problems when you're first doing them. But g prime of x is going to be 2 because it's just, we're going from power, we're just following the power rule, and we know that the derivative of a constant. So we'll say that d dx, we'll use c. Just remember that c stands for constant, is always going to be 0, and that's because there is not a slope to a constant function. We're taking the slope of the slope, but our slope is 0 in that situation. So now we're going to add f prime of x, which is just going to be take the 2 down, multiply it by the x, subtract the 2 from the exponent, which gives us 2x, and then we're going to multiply that by g of x. So 2x plus 3, which is going to give us 2x squared plus 4x squared plus 6x. And we can factor this and simplify it further by taking out a 2x from every term, which will give us 2x times x plus 2x plus 3. So now let's just try, if I asked d dx of x squared times 2x plus 3. So now I'm going to show you, I'm going to verify my answer, which is this right here. So if we wanted to multiply this out first, then we'd have to do it before taking any derivatives. So this would give us 2x cubed plus 3x squared. It's going to give us 6x plus 6x equals 12x. And as you can see, that's a very different answer from what we got up here. Wait, no, hold on. That's right. Just kidding. I misspoke and mistaught. So erase that from your minds. 6x squared plus 6x, which if we simplify it up here, I forgot to do that. That was my fault. That would give us 6x squared plus 6x. So either way does work. This is just meant to verify this. I just wanted to kind of show you guys that math is going to be the same no matter how. Like, it's not going to change because it's called calculus instead of algebra. We still have to follow the basic rules of, order of operations like PEMDAS. So this is just the product rule. I'm going to do a quick rundown of the next thing, which is going to be the quotient rule, which is different from the difference quotient. Someone asked that earlier. They were in the last session, and now I will go into the quotient rule to kind of show you guys just how different those two things are. So the quotient rule is how we take the derivative of a function like this. So we've got two functions, f of x and g of x, but they're written as a fraction, like f of x over g of x. So the way we take this derivative is, gosh, I hate this thing so much, but it works so well. It's like, no, I'm not going to do that. That's dumb. Look, I'm not going to yodel, because every calculus teacher ever will tell you have to yodel. They'll say you have to do like low D, high D, low, high, something like that. But I just know it because I didn't want to have to memorize that yodeling thing. So minus, I didn't see it right. I think it might have been plus, but yeah, no, I'm right. Why would I second guess myself? It happens to the best of us. Over g of x squared. Okay, so this is how you take the derivative of a fraction. Like, of a fraction of two polynomial functions. So for instance, let's say, I probably have a pretty good textbook example here, actually. Oh gosh, I literally just did almost a problem identical to that. So, oh, that's cool. All right, so we'll do this one after that. Yeah, I guess I'll just do this one. So this is straight out of the textbook. So this should be, if you can do this, you should feel pretty good about yourself. X squared plus 1 over 2x minus 3. Yeah, the reason I was hesitant to do this one was because it looks almost identical to the problem we just solved just with division. Because I did 2x plus 3x squared on that last problem. So this right here, we're going to identify our variables, or not variables, our statements, our open statements, which is a math phrase for when you've got an expression that doesn't have a defined x value. If you take a proofs class or discrete mathematics, which is a lot, if you're a computer science major, you have to take it, you'll learn a lot about that stuff. But we've got two open statements, f of x equals x squared plus 1, and then g of x equals 2x minus 3. So now we're going to take the derivative of those before we start, just for, I don't know, just because it's easier, I think. It's easier to show you guys that way. Okay, so nothing too horrible there. So now let's just set it up in this form. So we want to start with f prime of x, which is going to be 2x. Then we're going to multiply that by g of x, which is 2x minus 3. We're going to subtract f of x, which is x squared plus 1 times g prime of x, which is just 2. And we're going to divide the whole thing by g of x to the second power, which will give us 2x minus 3 squared. So most professors will not allow you to leave it this way, but this will at least get you like half credit. You should always simplify your answers. I don't know why people choose not to do that. 4x squared, I know my head's blocking it, I'm sorry for that. 6x minus 2x squared minus 2. 2, 4x squared minus 6x, that checks out. All divided by 2x minus 3 squared. So let's cancel some like terms, and that's going to give us 2x squared minus 6x minus 2 all over 2x minus 3 squared, which, let me double check this. Yeah, so I mean, you could leave it here. If you FOIL this one out, it's not going to get you any further. It's not going to cancel anything, but this right here, most professors would accept this as a finalized answer. I mean, some professors might ask you to just do the, 2x minus 3 squared, but probably not, because I think that is fully simplified, but they might ask you to work it all the way out, and you probably should 90% of the time, but if you just know how to factor and FOIL and you know that that's not going to work before it happens, like I knew before working this problem that this 2x minus 3 squared was not going to be able to cancel with anything on the top. And you'll develop kind of an instinct for when you need to do more work and when you need to do less. But since you are all Calculus 1 students, I can guarantee you that you're going to need to do more work. Like this class is really just kind of a brutal gateway into STEM careers because Calc 1 is like the first time you'll ever be exposed to kind of higher level math that's going to be combining everything you've learned priorly. So that's why I always say repetition and study the fundamentals, study graph shapes. You really just got to know it all. I mean, not all of it, because you guys are soon going to learn that there's a lot more math beyond calculus, but you should always kind of take into consideration those types of things. Like, you should definitely be doing this a lot. Because if you're not doing like an hour of practice a night, it's going to be kind of hard to stay with the class, at least pace-wise. So the next thing we're going to be looking at is, gosh, this one, they don't even teach it anymore, but it's a very useful trick to know. So this is the derivative of a reciprocal function. The reason they don't teach it is because it's not quite that broad. So it's like, you know, it's not going to be used a lot, but when it is used, it's very, very useful. So I'll just go over it real quick. If we've got the derivative for 1 over g of x, right? So this is just like the quotient rule, but this one's for a reciprocal, which means that it's a function underneath a 1. So that's going to be equal to the negative derivative of g of x over g of x squared. So for instance, if we have, let's just do a quick example here. If we've got the function 1 over x squared plus x, then we know that g of x is equal to x squared plus x, and we already know how to take the derivative of polynomials. So we'll use the power rule here, and we'll get 2x plus 1. So then, if we just plug this into this formula right here, we just have to put a negative sign in front of it, in front of the whole expression, not just the 2x. It's 1 over x squared plus x squared. Yeah, so that's how you take the, and I'll simplify it just because I kind of went on a tangent about that earlier. And that's this again right here. This is just me wanting to simplify more, but this right here is a perfectly acceptable answer. Like, if not better. I think this is a nicer format, but I know that a lot of you guys, like, not a lot maybe, but I know a good bit of you probably have like learned some bad habits in high school, I guess, because I know a lot of people that take Calculus 1 are freshmen or early years, but I'm going to break your bad habits because eventually we're going to get to a point in the semester in which a lot of you will need me to do problems in the group chat, and I will ask you to send work when you do them, because I would like people to at least attempt problems before they send them to me, but I understand that that can't always be the case because some problems are pretty rough. But the number one thing I'll be looking at when I'm solving your guys' problems is simple mistakes, because that's what 99% of mistakes are in math. That's always going to be like you forgot a negative sign or something like that. It's never going to be like, you know, this is pretty easy stuff to learn in calculus. It's the algebra that gets everyone. The concepts, the big picture concepts are not that bad, but the algebra is always what gets people. So with that in mind, let's take a look at some algebra. Not like high school algebra. This is like cool algebra. This is the first time you'll really see I think they call this the chain rule. So this is the first kind of big picture concept that you'll need to work on, because a lot of people have a hard time understanding this procedure right here. And there's a reason for it. I mean, it's not an easy concept to understand right off the bat. So let's say we've got a function. So if I've got two functions, right, like square root of 4x plus 1. So if you guys remember from your algebra classes, taking the square root of a function is the same as raising it to the 1/2 power. So now I've got this function, and then I've also got to deal with that half power. So we could write this as f of g of x, in which f of x is equal to the square root of x, and g of x is equal to 4x plus 1, which is the function on the inside. So let's just apply some basic derivative rules, right? So the way you're going to want to approach this is you're going to want to take the derivative of the outside first. So we take the derivative of the outside, multiply it by the inside, and then no, I'm going to explain this a different way. I changed my mind because I'm going to explain this while I'm working it. I'm going to explain it after I work it because that's how I like to do things. So we'll just follow the basic rules of derivatives. So we got the power out there, right? So we're just going to follow the power rule, bring that out front. We got that times 4x plus 1, now to the negative half, and then we multiply by the derivative of the inside, which is 4. So that 1/2 is going to cancel with that 4, which is going to give us 2. So then we will get 2 times, oh, you know what? Here, this is an example of some good simplifying. That's to the negative power, and it's to 1/2, so it's the final answer would be 2 over 4, the square root of 4x plus 1. So that right there probably looked like a lot that I did very fast, but now I'm going to go back and explain how I was able to come to this answer. So this is called the chain rule. And this is a very, very powerful technique in this class. It's going to be used the entire course. So if you don't like it now, you should start practicing and get comfortable with it. I'm just going to do a quick rundown and then we'll call it a day for the session because I just kind of wanted to go over some brief topics, and then on Thursday and Sunday, we'll kind of like nail in the repetition, and we'll just I'll do a Microsoft Teams like OneNote that we can write on together so you guys can work on problems and I can go through and check them while you're working them. But the process that I used here is we did f prime of g of x times g prime of x. Or you could say derivative of the outside times the inside, derivative of the outside, leave the inside plane, and then times the derivative of the inside. So if we've got something like, let me think, x times x cubed plus 3 to the 4th. No, we'll just get rid of this x because that's going to be a little bit too much. So take the derivative of the outside first, right? So it's to a power, so we can apply our power rule here. So now we're going to get, this is step 1 right here, so we'll go from that to 4 times the inside. And we're not changing anything on the inside first. The first thing we're going to be doing is looking at the outside, which is why I brought that 4 out front to multiply this and then reduce the power by 1. So now we're going to be looking at the inside. And we're going to multiply the first bit, the derivative of the outside, with the regular inside times the derivative of the inside, which is just going to be 3x squared. So we can simplify this even further and get 12x squared. That's just me multiplying this 4 and this 3x squared here times x cubed plus 3 to the 3rd power. Okay, that is all the time I've got for today, guys. I hope this was helpful. If you want stuff to practice, I know we've got a test coming up. I would definitely recommend the chain rule. If you don't understand the chain rule, I would work on the quotient rule and the product rule and the power rule. And then once you've worked through like all of those problems and you feel very comfortable with all 3 of them, then you can move on to the chain rule. Because this is really like, you need to understand the basics of taking derivatives before you can apply more advanced concepts like this. So next session, Thursday, will be same time as this one, 5 p.m. And it's going to be much more problem-based. So I'll probably make a worksheet sometime this week. And then I can either post it before the session or during the session. It'll be based off what you guys want me to do. But that's all I got for today. I hope it was helpful, and I am looking forward to seeing you all on Thursday.